What is the source of matter inside the atom? What is the source of matter inside the atom? The protons and neutrons, right? The protons and neutrons, I shouldn't say matter. I should say, let me replace that here. I should say mass. Protons and neutrons provide the mass of the atom. Whether that atom is oxygen or whether that atom is carbon, their mass comes from their protons and neutrons. We've also stated that the mass of a proton is roughly equivalent to that of a neutron. So, if we were to think of our carbon-12 atom, it has 6 protons and 6 neutrons, or we could say 12 mass-bearing particles or mass-contributing particles. What if we had a conversion factor that let us convert the number of protons to a mass in grams? And we do! Drum roll, please, for the most quintessential moment of your life this far. Introducing the mole. It turns out that 6.022 times 10 to the 23rd protons has a mass of 1 gram. That means that since a proton and neutron are roughly equal in mass, that's 6.22 times 10 to the 23rd neutrons also have a mass of approximately 1 gram. This number, this 6.22 times 10 to the 23rd number, is so important that we've given it a special name. We refer to 6.022 times 10 to the 23rd of anything as a mole. The mole is simply another name for 6.022 times 10 to the 23rd. For example, everybody's familiar with a dozen. When I say that you have a dozen something, you know that you have 12 of it. When I say you have a mole of something, you have 6.022 times 10 to the 23rd of it. If I say you have a score, referencing the Gettysburg Address here, you know a score is 20. If I say you have a score, you have 20 of it. If I say you have a mole, you have 6.022 times 10 to the 23rd. You've done any construction or hardware work, you know what a gross is. If I say you have a gross of something, you have 144 of it. Same way for the mole. If I say you have a mole, then you have 6.022 times 10 to the 23rd. Mole is simply a named number. And this named number is important because it's the number of protons in 1 gram. Now where does this get us? Where does it get us? It nearly gets us all the way through the Death Star's trench, just like Luke Skywalker. Why won't you write down Luke Skywalker? Write down Luke Skywalker. I hope everybody's writing down Luke Skywalker. The mole is so incredibly important. This 6.022 times 10 to the 23rd is so incredibly important that we give it 2 names. We call 6.022 times 10 to the 23rd, we refer to it not only as a mole, but you'll also hear it referred to as Avogadro's number. This is where it gets us. If I have 6.022 times 10 to the 23rd carbon-12 atoms, or if I have 1 mole, is another way to put it, of carbon-12 atoms, then I have 6 protons and 6 neutrons. And we said that whenever we have 6.022 times 10 to the 23rd protons, we have approximately 1 gram. Whoops, I wrote neutrons twice. I mean protons twice. And whenever we have 6.002 times 10 to the 23rd neutrons, we have approximately 1 gram. So we have 6 grams of protons and 6 grams of neutrons, or 12 grams of carbon atoms. If I have 1 mole of carbon, then I have 6 moles of protons, 6 moles of neutrons, each 1 gram, or 12 grams. What this magic number, 6.022 times 10 to the 23rd, does is it lets me read the atomic mass off my periodic chart in grams. So, for example, if I have 1 mole of hydrogen atoms, then I have 1.0079 grams of hydrogen atoms, because I can read that mass right off the periodic table. I can read that number right off the periodic table in grams now instead of AMUs. Another way to think about it is if I have 1 atom of nitrogen, what's its atomic mass? 14.0067 AMU. If I have 1 mole of nitrogen atoms, then I have 14.067 grams of nitrogen atoms. If I have 6.022 times 10 to the 23rd nitrogen atoms, then I have 14.0067 grams of nitrogen. If I have 1 mole worth of atoms, then I can read that number off my periodic table in grams. This is an unbelievably useful tool because it provides us a conversion factor between atoms and grams. Let's make sure this horse is thoroughly dead. What is the mass of 1 mole of oxygen atoms? No thinking, just go to the periodic table and read the mass number, 15.9994 grams. So the mole allows me to read that number off the periodic table, not in AMUs, but in grams, which is an awesome, awesome tool. Couple new definitions now. The mass of 1 mole of a substance is referred to, correct the spelling of referred on your own paper, is referred to as the molar mass of the substance. For example, What is the molar mass of carbon? The molar mass of carbon would be the mass of 1 mole of carbon, so it would be 12.011 grams per mole. A synonym for molar mass is gram formula weight. Even though we're dealing with a mass here, for some reason the term is always gram formula weight. You'll see it abbreviated in textbooks, GFW, or a lot of times you'll be reading a paper. I see it a lot again in biochemistry where you're reading a paper and they're talking about a protein and you'll see a number after the end of that protein in parentheses and it'll say GFW. They're talking gram formula weight, and that's a synonym for molar mass. So if I asked you what the gram formula weight of carbon was, you would say 12.011 grams. So they're pretty similar. Notice that slight difference in the unit, right? Molar mass, we gave the units by default as grams per mole, whereas when we're talking gram formula weight, we leave the units just in grams, and that's the hair split difference there. Somebody who never bothered with hair split differences was Han Solo. Why don't you write down Han Solo? Write down Han Solo. What's a pirate's favorite element? Argon! Let's use this simple question here to illustrate the usefulness of the power of the mole. How many moles of argon are in 42.2 grams of argon? We're going to treat all these problems just like a unit conversion because that's all they are. This really isn't anything new. From this point forward, we're just doing those same things we did the first day of class where we were going from kilograms to grams. We're going to go from grams to moles in the same fashion. If we read this problem, how many moles of argon and 42.2 grams of argon, we have one number with which to start our line, 42.2 grams. It's important from this point on in the semester that you never just write grams or never just write moles. You always write grams of, moles of. So my unit here isn't just grams, it's grams of argon. Do I want grams of argon? No! I don't want grams of argon. So I'm going to place grams of argon down here where they cancel out. What do I know about grams? The only thing you ever know about grams is the molar mass. It's the only thing you ever know about a substance is grams. If we go to the periodic table and locate argon, number 18, we see that 1 mole of argon has a mass of 39.948 grams. That is our conversion factor. What the periodic table tells us is our conversion factor between moles to grams. It's our molar mass there, right? So, back to my line. I place moles up here, 1 mole. Place grams down here where they cancel out, and that's a 3.948. Hey, I've canceled out my grams. I'm left with units of moles, which is the unit they're asking for in the problem. So I multiply everything on top, divide through everything on the bottom, and I get 1.06 moles of argon. Chemistry's easy, life is hard, right? All right, if we can go forwards, we can go backwards. How many grams of argon would there be in 0.22 moles of argon? This time we're starting our line, again, with the only number given to us in the problem. And we know that our first step has to involve getting rid of moles of argon. What's the only thing I ever know about moles? Well, I know several things about moles. Let me rephrase that. What do I know about the relationship between moles and grams? I know the molar mass. I can get that from looking at the periodic table. So if I come over here and I look at the periodic table, it tells me that 1 mole of argon has a mass of 39.948 grams. So 1 mole Notice, pay attention, I've canceled out my number of moles. Notice, again, my setup is the exact opposite as it was in the previous problem. There's no rule that says one always goes above or below the line. Just like with we were doing with our grams and kilograms, write the relationship 1 mole equals and keep the numbers with their units. 39's in front of grams, so I keep 39 in front of grams here. 1's in front of mole, 1 in front of mole. I multiply everything on top, I divide through by everything on the bottom, and I discover that 0.022 moles of argon has a mass of 39.948 times equals oh, whoops, my calculator lie is that I've got 2 sig figs there, so 2 sig figs in my answer, rounding the basis of that, and I get 0.88 grams of argon as my answer. Chemistry's easy, life is hard, yes? All right, how many atoms of arsenic in 3.3 moles of arsenic? All right, let's start by drawing our line. We've only been given one number in the problem, so we know that that has to be what we start with. I start with moles of arsenic, so I also know my next step is going to involve getting rid of moles of arsenic. What's the only thing I know about moles of arsenic and the relationship to atoms? Well, by definition of a mole, I know that 1 mole of anything, arsenic, turnips, or baseball players, is 6.022 times 10 to the 23rd of it. So 1 mole of arsenic is 6.022 times 10 to the 23rd atoms of arsenic. Why is that? It's by definition of the mole, right? That's the definition. 1 mole, 6.022 times 10 to the 23rd. Since our frame of reference is arsenic atoms, that's where we can attach those units. I've canceled out my number of moles. I multiply everything on top, divide through by everything on the bottom, and I get 3.3 times 6.022 to the 23rd, and that gives me 1.99 times 10 to the 24th atoms of arsenic. You know who would be too cowardly to use arsenic? C3PO. Why don't you write down C3PO? I hope everybody's writing down C3PO. All right. How many moles of mercury in 8.7 times 10 to the 19th atoms of mercury? Here what we're doing is we're going backwards. We've got 8.7 times 10 to the 19th atoms of mercury. Even if I have no clue how to work the problem, I know my first step is going to involve getting rid of those atoms of mercury. What do I know about atoms? I know the relationship between atoms and moles, because by definition, 1 mole of anything is 6.022 times 10 to the 23rd of it. So, I now know a relationship. I keep the numbers with their units. I multiply everything on top. I divide by everything on the bottom. And that gives me moles of mercury. And if your calculator is not in scientific notation, why don't you write down R2D2? Write down R2D2. Everybody's writing down R2D2, I know. Write down Darth Vader. Write down Darth Vader. I hope everybody's writing down Darth Vader. But in the meantime, let's kick this party up a notch. Let's party like we're Sith. We're faced with a problem. Once again, that problem has 1 number in it, so we know we're going to start our line with it. We also know that whatever our first unit is, we're going to get rid of it. What do we know about grams? The only thing we ever know about grams is molar mass. Our periodic table, if we look up calcium, calcium's number 20, and you'll see that 1 mole of calcium, according to the periodic table, has a mass of 40.078 grams. So, I'm going to keep the numbers with their units. 1 goes with moles. 40.078 goes with the grams. So I've canceled out my grams. I've gone from grams of calcium to moles of calcium. Now, this problem's not asking for moles. It's asking for atoms. Do we know a relationship between moles and atoms? Yes, by definition of the term atoms. For example, well, not definition of the term atoms, by definition of the term mole. We know that 1 mole of anything, hammers, baseball cards, pizzas, 1 mole of anything is 6.022 times 10 to the 23rd of it. So I know that if I have 1 mole of calcium, I have 6.022 times 10 to the 23rd atoms of calcium. So I'm going to place moles where they cancel out. Place atoms where they'll be left. Keep the numbers with their units. Multiply everything on top. Divide through by everything on the bottom. And I punch that into my calculator. I get... Somebody stole my calculator. I get 20.22 divided by 40.078 times 6.022 second EE to the 23rd. And that gives you 3.038 times 10 to the 23rd atoms of calcium. Chemistry's easy, life is hard, yes? Let's try another. How many grams of scandium are in 9.2 times 10 to the 29th atoms of scandium? All right, I've only got one number to start my line with. 9.2 times 10 to the 29th atoms. I don't want atoms. I need my atoms to go away. Well, I don't need my atoms to go away, then I'd stop existing. But anyway, I'm going to place atoms where they cancel out. What do I know about atoms? Well, I know their relationship to number of moles. I know that 1 mole of scandium contains 6.022 times 10 to the 23rd atoms of scandium. So 6.022 times 10 to the 23rd atoms of scandium in 1 mole of scandium. I don't want moles of scandium. So I've gone from atoms of scandium over here to moles of scandium over here. I don't want moles of scandium, so I know I'm going to get rid of moles of scandium. What do I know about scandium? Well, because I watch Netflix. No, I'm sorry. I know that moles of scandium, I know that 1 mole of scandium, according to my periodic chart, is 44.9559 grams of scandium. So 1 mole of scandium, 44.9559 grams of scandium. I multiply everything on top. I divide through by everything on the bottom. And I get, let's see here, 9.2 second EE 29 divided by 6.022 second EE to the 23rd times 44.9559 equals 2 sig figs, 6.9 times 10 to the 7th grams of scandium. Chemistry's easy, life is hard. One for old time's sake. How many atoms of nitrogen in 3.14 kilograms of nitrogen? Well, we've got one number to start our line with. 3.14 kilograms of nitrogen. Well, I know I want to get rid of kilograms of nitrogen. And I know, because I studied those prefixes hard, that 1 kilogram of anything is 10 to the 3rd grams of it. So I can convert kilograms of nitrogen to grams of nitrogen. All right, and once I have grams of nitrogen, I know the pathway to get to atoms. Because if I can go to grams, I know I can go to moles. I know that 1 mole of nitrogen atoms, according to my periodic chart, is 14.0067 grams of nitrogen. I have grams here, so I'm going to place grams here where they cancel out. I want moles. I keep the numbers with their units. I've crossed out grams. I've gotten moles. I don't want moles, though. That's not what they're asking for. So I know in my next step, I have to get rid of moles. By definition, I know the relationship between moles and number of atoms. Just for kicks and giggles, it might tickle the people here listening that I have somebody at this table trying to very hard to work math problems in silence as I holler out these random numbers. So I know that 1 mole of nitrogen is 6.022 times 10 to the 33rd nitrogen atoms. So I'm going to multiply everything on top, divide through by everything on the bottom. Why am I done? because I have the unit I'm looking for, right? Atoms of nitrogen. Multiply everything on top, divide through by everything on the bottom, and I get 3.14 times 1,000 divided by 14.0067 times 6.022 times 10 to the 23rd. And survey says 3 sig figs 1.35 times 10 to the 26th atoms of nitrogen. And that concludes today's awesomeness of lecture.
And he was blurting out